Okay, so the first question says, multiple choice questions on a test each have 4 possible answers, one of which is correct. Assume that you guess the answers to 5 such questions. So on any given question, what is the probability that you get the answer correct? It's 25% or 1 out of 4 or 0.25. What's the probability that you get any question wrong? 0.75 or 3/4. Okay, use the multiplication rule to find the probability that the first 2 guesses are wrong and the last 3 guesses are correct. That is, find the probability of WWCCC, where C denotes a correct answer and W denotes a wrong answer. Okay, so what's the probability that the first question is wrong?
3 out of 4.
3 out of 4. What's the probability that the second one is incorrect?
3 out of 4.
And then we have 3 correct ones after that. That is 1/4 times 1/4 times 1/4. Okay, and when we calculate this, what is our answer? All right, you guys calculate the answer there. I have the answer.
Oh.
All right, 0.00, and I think rounded to 4 decimals, I think it's 0.88. Is that right? Okay, make a complete list of the different possible arrangements of 2 wrong answers and 3 correct answers. So this is where we do, just like the boys and girls, we're going to make an organized list with 2 W's and 3 C's. Okay, when you can do this with a tree diagram, or you can actually just have your W's go through the list one at a time. So I will keep the first one in place and move the second W one to the right. So one at a time. So I end up with WC, WCC. The next one would be WCCW. And then WCCCW. Now that I have reached the end of my list, I actually move both of them to the next place. Meaning my first one is going to be C, then I have 2 W's, and then 2 C's. I keep my first one fixed again, and I move my second one through the list. It's just one way to make sure that I don't count anything twice and I don't leave anything out. And CW, CCW, again I'm at the end, so I now move both W one place to the right, and then move the second one again until I get to the end when I move both of them. So how many different choices do we have over here? Well, we end up with a total of 10 different combinations, right? This would be, we can use our combination rule. We can look in how many ways can we have 2 wrong and 3 correct. So it's 5, choose 2. Or 5, choose 3 if we're looking at the correct ones. So it says over here, so this is our list for part B, and for part C it says, based on the preceding results, what's the probability of getting exactly 3 correct when 5 guesses are made? So this was one particular order, right? The second part we calculated in how many ways can we have 2 wrong and 3 correct. And now for part C, we're actually putting that together. So what's our probability? So it's going to be 10 times, because we have 10 different ways of making 2 W's and 3 C's, and each one of them has the same probability of 0.0088. So that was the binomial probability formula, which tells us the first part, the NCR, or NCX tells us in how many ways can we have 3 correct ones among our 5. So that would be 5 choose 3, or 10. And then looking at one particular order, this is P to the X times Q to the N minus X. Where in our example, that would be 5, choose 3, because we want 3 correct, times the probability of correct is 1/4 to the 3rd power times 3/4, 3 of them being wrong, to the 2nd power. So it's just 10 times that individual probability, which just moves the decimal point 1 place to the right. And our probability is 0.088. So first part tells us in how many ways can we have 3 correct, 2 wrong. And the second part looks at that one specific probability for 3 correct questions and 2 incorrect. All right, and then number 3 is actually very similar. So we'll go over number 3 and then come back to number 2, just so hopefully it makes sense when we do a second example. So number 3 says, suppose that in one town 10% of people are left-handed. Suppose that you want to find the probability of getting exactly 2 left-handed people when 4 people are randomly selected. Can the answer be found as follows? Use the multiplication rule to find the probability of getting 2 left-handers followed by 2 right-handers, which is 0.1 times 0.1, so the first 2 people being left-handed, times 0.9 times 0.9, which is the second 2 people being right-handed. If not, explain why not, and show how the required probability can be found. So again, number 3 is very similar to number 1. What did we forget in number 3? Because this is the probability that the first one is left-handed, the second one is left-handed, and then the third one is right-handed, and the fourth one is right-handed. So this is the probability of left, left, right, right. We want to know what's the probability that exactly 2 of our 4 people are left-handed. So it wouldn't have to be in that order, that's right. So we actually would have to look at all the different cases again, right? In how many ways can we have 2 left-handed and 2 right-handed? Well, if we're looking at the combination, do you know how many ways we can have 2 left-handed, 2 right-handed? How many people total? 4, that's our N. How many are we looking for that are left-handed? 2. Right? So it's 4 choose 2, 4C2. When we're making our list, that's going to be, right here, let's make a list. So we have left, right, right, left. I'm going to do the same thing I did before, just making an organized list. Right, left, left. So there's 6 different ways. So what is the probability?
It would be 6 times 0.1 squared times 0.9 squared.
That's it. So 0.1 squared times 0.9 squared, that is your probability of success times the probability of failure. And then the 6 tells you in how many ways can you have 2 successes and 2 failures. So that is the binomial probability formula, which is not the only way to answer a question like that. We could actually have used the binomial PDF here as well. All right, so our answer in this case is, what is 6 times 0.1 squared times 0.9 squared? Rounded to 4 decimals, that's approximately 0.0486. And you can check your answers on your own. So this is probably the most complicated part of doing probability, is actually using that probability formula. Yes, Kyra?
So, how do you get when you find the different outcomes?
Okay, how I find the outcome, I'm going to start with my 2 L's here, and then I keep one in place and I move the other one over. Okay, when I get to the end, I'm going to move both of them over to the right. And then keep this one fixed, move the other one over. Until I get to the end, that's when I move both of them. I stop when my 2 are at the end. So it's a way to make sure that I get all of them. Another way to doing it is you could do a little tree diagram, right? First one could be left or right. Second one could be left or right. Third one could be left or right. And the fourth one could be left or right. And then at the end, you have all the different possibilities, right? You put them all together. It's going to be in a different order than the list I made, but it will have all the possibilities.
So you're ending with the beginning.
Well, I only looked at the ones that had 2 left and 2 right. So if you're making a whole tree diagram, you would have to pick out the ones that actually have 2 left and 2 right, because this gives me the entire sample space. So doing it this way is just a nice way to make sure you're listing them out. It also is helpful to figure out how many you will end up with at the end. So since we have n is 4 and 2 are left-handed, you know you're going to end up with 4C2 total combinations at the end. So you could just figure out, 4C2, that's equal to 6, so I'm going to have to multiply 6 times the probability of success times the probability of failure. Again, it's a binomial distribution, and we could have used the binomial PDF instead. Make sense? Hopefully, somewhat, a little bit. I know this is the binomial probability formula is complicated. It's a lot more complicated than using the binomial PDF. So we will get to some examples of that as well. All right, let's go back to question number 2. Question number 2 says, suppose that a class of 30 students is assigned to write an essay. First part, suppose 4 essays are randomly chosen to appear on the class bulletin board. How many different groups of 4 are possible? And then the second part says 4 essays chosen again, but for awards of $10, $7, $5, and $3. So you can see the similarity with the question, but also the difference, right? The question you must ask yourself is, does the order in which I pick these matter or not? And when you're answering a question like that, you're going to say, are they treated the same way or not? So in this example over here, for part 1, all of them are going to appear in a bulletin board. Does it matter which order I pick these essays in? No. So part 1, order doesn't matter. And on a lot of the questions I'm actually asking you, does the order matter? Just so you understand, if the order doesn't matter, that means it's a... What kind of problem? A combination. Okay, we have n given and we have k given, right? What's n? 30. And it's a combination, so it's a C. And what's k? 4. So what is 30 C4? Okay, so 30, remember math probability, combination 4 is 27,405. Absolutely. So that's the first part. Second part, now we're treating them differently. So yes, does the order matter for part 2? Yes, because you'd rather be picked first than last, right? Because you're going to be treated differently. Yes, Kyra.
How did you go to what was the combination for the
So you first put in the 30, then you go to math, probability. So math, error over to PRB, go down to option 3, put in the R. So that's NPR, or NCR rather. Okay, so the second part, yes, order matters because each one is treated differently. You have different rewards, different positions. Therefore, it is now a P, or permutation. Other things where order matters is like if you're rearranging letters, or you're rearranging numbers to make like a combination or something like that. All those are examples of permutation. So n is still the same. So this time it's 30p4. R is still the same. You're going to find it very similar by putting in first the n, then going to math, probability, NPR, and putting in R4 as R. And we now have more combinations, because when the order matters, you're always going to end up with a larger number. So 657,720. So don't feel bad if yours wasn't picked. A lot of different combinations. All right. So please, for any of the combination or permutation questions, ask yourself, does the order matter or not? All right, for number 4, this is table probabilities. You always want to separate the totals from the rest of the table, and sometimes you're not actually given totals, so you may have to find the totals yourself. Over here, when we looked at table probabilities, and you all, did the examples on your sheet, hopefully, we have different types of questions. We may be just looking for one answer, or we may be looking for one or the other. Whenever we have or, we're looking at highlighting both, and anything highlighted would be in our sample. And is the other possibility, that's where we highlight, and our overlap is what we're looking for. And then the last one is the given probability. This is the only